Welcome to my talk on high-performance XPU Stencil Computations in Julia. I'm Omlin, computational scientist and responsible for Julia computing at the Swiss National Supercomputing Center, ETH Zurich, and my co-author is Ludovic Räss, also from ETH Zurich. In high-performance computing nowadays, people often mention the 3 Ps: performance, portability, and productivity. More specifically, one might understand the 3 Ps as scalable performance, performance portability, and productivity. Everybody agrees, it's a challenge. In this talk, we will present you one part of our solution to this challenge. To be more precise, in order to perform large-scale high-performance computing, we will address the questions noted on the right. Now, in this talk, we will focus on the single-node performance. So to do so, we of course also need to give you our answer to the question about performance evaluation and programming languages. I colored the 3 Ps in red, green, and violet. On the right, I will introduce our solution to this talk's focus, using then the same colors to show you what each aspect of the solution addresses. Okay, so first, which programming languages do we use? Our language of choice is fast, just ahead of time compiled as an LLVM-based compiler, is simple, high-level, interactive, and development cost is low. Of course, I'm talking about Julia. Then, how do we achieve a good single-node performance? Our solution is automatic parallelization and optimization of architecture-agnostic code. The package file Stencil does that for Stencil Computations. Finally, how do I evaluate performance in an absolute manner in order to get an idea of how much room for improvement there is? Until the beginning of this century, the performance of a scientific application was normally bound by the speed at which the hardware could do floating point operations, flops. Thus, performance was evaluated flop-based. Meanwhile, it's most often memory access that bounds the performance of scientific applications, because the amount of flops that can be done per memory access has drastically increased and is ever growing, as you see in a plot. We therefore want to do memory throughput-based performance evaluation. And our solution is an effective memory throughput metric to evaluate the performance of stencil-based iterative solvers. Now here you see the summary of this introduction. I presented you already the 3 P challenge we want to address in this talk. Now I'm going to present you a simple nonlinear example that will later to illustrate our solution to this challenge, 2D glacier flow. Then I will show how Stencil responds to this 3 P challenge. Finally, I will quickly remind the effective throughput metric and the report results and finish with conclusions. These two equations describe the glacier flow. H is the glacier height, QH are the fluxes, P is the topography, G is the gravity, and mu the viscosity. You can see that this describes a nonlinear diffusion. Here you see the essential part of the code that enables to simulate the glacier with these equations. It uses implicit time stepping. You can see that we have a time loop with sub-iterations in which we compute the flux and update H. It employs the pseudo-transit method and numerical damping for faster convergence. You can find more information on the pseudo-transit method in this paper here. Parallel Stencil. Parallel Stencil is designed for domain scientists and has proven to be very well suitable by domain science students. It allows to write architecture-agnostic high-level code for parallel high-performance stencil computations on GPUs and CPUs. It relies on the native kernel programming capabilities of CUDA.jl and on base.threads. Now I will show you how to apply parallelization to the glacier flow curve. First, we initialize the parallelization with CUDA as thread, calling in parallel stencil. Then we allocate our arrays with macro serials, which will then automatically allocate either C arrays or normal arrays depending on the chosen above. A side note, the keyword argument cell names and cell type allow to allocate the logical arrays of struct, or small arrays, leveraging cell arrays, which internalize some static arrays. This allows to easily switch back and forth between array of struct or struct of array allocation. Here you see now the main part of the code. The difference compared to before are highlighted in red and yellow. In the compute function, we use macros instead of functions, and we have the macro parallel in front of the function definition and the function call, and that's it. The parallel macro then automatically generates parallel high-performance CPU or TPU kernels, and TPU kernel launch parameters are derived from the kernel arguments by analyzing the array extension. Parallel indices allows to write explicit kernels. One chooses the indices, here ix, iy, and then just writes an explicit kernel as you see here. This allows us in this example to avoid storing the fluxes in main memory and instead just recompute the flux values on the fly whenever we need them. Note that there is also a basic set of architecture-agnostic low-level kernel language constructs available. For example, for explicitly control the shared memory of a GPU. Supporting many low-level constructs is absolutely not the target. Instead, we have a kernel abstraction.jl backend on the roadmap. And then most or all kernel abstraction kernel constructs should just become straightforwardly supported. While Stencil allows to automatically hide communication and computation, it's done as follows. It splits the inner point and the boundary computations and launches them into two different streams. And then as soon as the boundary computation is finished, it triggers the communication. Here you can see the timelines of the communication and computation routines of a run with CUDA MPI on a single node with 4 NVIDIA Tesla V100 GPUs. And they were connected with NVLink, so this means that the communication with MPI is using NVLink here. Here we zoom into 3, let's say 2.5 iterations. And you can see that the communication-related routines in purple overlap the computation routines in green. And data transfer happens on non-blocking high-priority streams. It's clear that the communication part will take much longer relatively for runs where we have more than one compute node. The effective throughput metric. First, we define the effective memory access AF. It is 2 times the unknown plus the known, where the unknown is the memory footprint of the unknown fields that depend on their own history. They need to update their iteration. The known is the memory footprint of the known fields. They do not change their iteration. Based on this, we straightforwardly define TF as AF divided by TIT, where TIT is the execution time per iteration. Finally, you can state that the upper bound of TF is Tpeak. The peak memory throughput as measured, for example, by stream for CPU and something analog for GPU. You wonder why we define AF that way? Well, it's simple. Because every iteration we need to read and write the unknown and only read the known. So for our glacier flow example, AF is computed as shown here, and X and then Y are the number of grid points that measure X and Y. Super important here, really crucial, we don't count, for example, fluxes, because they do not depend on their own history and can be recomputed on the fly and stored on chip. Results and conclusions. I will start with performance results from the nonlinear glacial flow. You can see that on the very left, with CPU array broadcasting without parallel stencil obtained 1 GB per second, whereas the peak memory throughput of the CPU used was 57 GB per second. Then with GPU array broadcasting achieved 149, whereas the peak throughput was 1055. Then using parallel stencil and with some convenience arrays to store the fluxes in main memory, we severely improve and obtain 26 and 634 GB per second. And then finally, with the best version, we get 37 and 1060. The primary reasons for CPU speedup with parallel stencil here in this case are multithreading and loop queuing. The primary reason for GPU speedup with parallel stencil in this case are probably better suited GPU kernels and launch parameters for these stencil computations and kernel fusion. Can we still do better? Certainly a bit, but at the very most 7% better. The ratio TF divided by peak is 93%. We have 2 applications from CUDA C to Julia using parallel stencil and implicit overfit. The first is a 3D portal with elastic two-phase flow solver, and the second a solver for 3D reactive porosity waves. They achieve 90 and 98% of the performance of the corresponding CUDA C applications. Now here we can see the parallel efficiency of the Julia 3D portal elastic two-phase flow solver in yellow and the original CUDA C solver in blue. Now, so far we run Julia code only up to 1024 GPUs, but you can see that we got a parallel efficiency greater than 95%. This is a great part thanks to parallel stencil's high communication feature. Again, very much thanks to the high communication feature, we achieved similarly good scaling results for a 3D nonlinear diffusion solver and a 3D viscoelastic Stokes solver, and obtained more than 96% parallel efficiency on up to 2000 and more GPUs. Now I'd like to highlight that Stencil is not limited at all to earth science or PDU solvers. At the PASC 21 conference, we presented our first multi-GPU solver with complex numbers implemented with Stencil in APC global grid. And at PASC 22, we presented our first image processing application implemented with Stencil. In the documentation of Stencil, you'll find many more multi-GPU application examples. Conclusions. I'll keep the conclusion very short. We show the Stencil response to the 3Ps. Thanks a lot for listening.